Today we will look at a topic named as a meta-classified hybrid fusion model for interference resilient modulation classification, which is a fast-growing area in wireless communication. As systems become more complex, there is a need of smart automated way to classify a signal type without human help, vital for application like cognitive video, military application, modulation classification, which is previously done with signal processing and is now faster and more accurate way using deep neural network that processes the raw signal effectively and noisy, making the communication system more reliable and different. Let's let's start by understanding the modulation classification and its importance. In this topic, automatic modulation classification using hybrid fusion model, we will start with an abstract, then introduction to the topic, followed by research methodology. Research methodology, we will discuss the steps taken to achieve the required results, and I will discuss the different BIM models and the host models and compare their performance. Then we will end the presentation with the conclusion and required reference. In the following study, we use a deep neural network which are effectively learn later information, enhancing the modulation classification accuracy. The method classified 24 RF modulation signal using deep neural networks. In this study, we have a signal analyzed using deep neural network. The signals have channel interference effects like carrier offset, phase offset, relay fading, and AWGN. The study examined the deep neural network techniques like VGT, RASNet, and CLDM and compare them. And we have proposed our own model named hybrid fusion model. The custom architecture accuracy is compared with existing approaches. The architecture approach improves robustness under different channel performance conditions. The main focus of the research is to propose a hybrid fusion BIM model that outperform the traditional automatic modulation classification techniques, especially in the low SNR, and achieve a higher accuracy and better processing efficiency compared to conventional methods that are the conventional models like VGT, LST, and GRU and CFD based methods that experience 30 to 40% performance from a challenging environment, whereas a hybrid fusion model maintain a performance under channel interference and has shown the improvement at low SNR for about 30 to 40% accuracy improvement, and at high SNR for about 10 to 15% accuracy improvement at high SNR. Following research have many practical applications. The wireless communication. Wireless communication is crucial for national security and enabling efficient and reliable communication in dynamic environment. Whereas automatic navigation classification of channel interference is essential for spectrum neutral communication radio. They play a vital role in many applications like satellite communication, electric communication, telemetry, mobile network, long-range communication, and many other applications. Now I will discuss the automatic modulation-based communication-based system. On the left side we have input data modulated and passed to antenna and transmitted to the air. In the air in the channel we have AWG and delay-based effects, and this signal is received from the antenna and due to receiver chain effects like receiver noise, carry offset being added to the signal. After that, the signal is passed to the automatic modulation block that will tell us about the level of the modulation scheme. Based on the level we will demodulate the signal. In the signal model, I will discuss the mathematical composition of signal that has been transmitted over the channel. The signal is impaired by adaptive Gaussian noise and delay fading. Therefore, the following formula can be used to express the signal where AM refer to the modulation amplitude and is the signal symbol sequence. FC is the carrier frequency, TS the symbol period, where FM is the modulation frequency, phi m is the modulation phase, and phi naught is the initial phase. Modulation class is represented by phi. Therefore, MFSK and MASK and MPSK is over here, where the when the signal is prepared, the carrier offset and phase offset and noise is added as per the channel interference effect. Now I will discuss the research methodology of the I use a reviewable data as a reference to initially train the model. This dataset consists of 24 modulation scheme, 26 different SNR ranges from -20 to +30 dB, with set size of 2 dB. In the research procedure, I followed the following steps. Initially, I have a dataset that is radio ML dataset. I created my own data set using the following statistics that are fc is equal to 0 to 2 millihertz step size, ranges from 0.02 megahertz, and phase offset minus 10 to 10 degree, step size of 2, whereas the frequency offset 0 to 5 kilohertz with a step size of 1k. These all channel interference effects are added to radio ML dataset. Then the TNN models are trained, and these dataset is trained into uniform train test split. And after that, the following models are trained, and then after that we use in the training we use different callbacks and compare these models using the following matrices that are accuracy, precision, recall, F1 score. I will discuss the different TNN model and their structures in the following section. The first model I trained was a BGG model. Following is the architecture displayed in the photo, whereas it takes input of 1024,2 and have 620 layers, 3 fully connected layers, and output 24 modulation scheme. And following are the configuration to train a model. The second model I trained was a LSTM based CNN model that takes the same input of 1024,2 IP data, has 3 quantity layers, 3 LSTM layers, 1 fully connected layers, and output 24 modulation scheme labels, and trained on the same configuration as VGG model trained. Third model I trained with the GRU CNN model, same input at 1024, IP data, 3 1D layer, 3 GRU layer, 1 fully connected layers, and output 24 modulation labels, and trained on the same specification as the previous model. CLDM, the hybrid model, takes an input same as 1024,2 IP data, 2 quantity layers, 2 LSTM layers, 1 fully connected layers, and output a 24 modulation scheme trained on the same configuration as previous models, but it's a hybrid model. This is our hybrid fusion models that contain all the previously trained 4 models that are VGG model, LSTM model, GRU model, and CLDNN model. The models are working in parallel. These all takes an IQ data of 1024,2 and outputs labels of modulations. These modulation labels are concatenated and passes to another model MLP hidden layers that are then outputs 24 modulation scheme classification labels. Now I will compare the accuracy metrics of different models under SNR and channel internet interference. At low SNR, we have seen that the hybrid fusion model maintain about 58 to 67 accuracy, while the baseline models like CLTN and GRU, STM, BGG stay below 12%. In a transitional SNR, phase minus 6 to 6 dB. Hybrid fusion model gives about greater than 99% accuracy at just 2 dB, where baseline models are struggling to classify the modulations, whereas in high SNR greater than 2 dB, hybrid fusion models sustain 99% accuracy, with the other models such as GRU ranges from 66 to 91% greater than 2 dB, whereas LSTM reaches from 64 to 90% greater than 2 dB, VGG 97 to 99%, and CLDNN 57 to 83% accuracy for higher SNR greater than 2 dB. Now we will compare other evaluation metrics like accuracy, precision, recall, and upper score of DNN models. Hybrid fusion models has an overall accuracy for 89%, VGG for about 78, and the other recurrent models like LSTM, GRU, and GRU models have achieved for about 60%, and whereas CLDNN performed the weakest, that is 52%. And the main key sites would be VGG perform reasonably good but struggles with dynamic invariants where the recurrent networks fails under noise and other channel interference effect. Hybrid fusion strengths come from temporal and spectral features and good in accuracy modulation classification. Now I will discuss the confusion metrics of the four DNN models under AWG and frequency offset and phase offset, in other words, channel interference. Whereas for BGG, we have seen the similar strong diagonal values. The AM SSP, SC, and OK has 87 to 73% accuracy, and slightly off the diagonal confusion as compared to hybrid fusion models, where have in LST and GRU CLDN, we have seen the most scattered misclassification, especially among QPS wave-com and 64-com, and has less effective under channel interference. We will discuss the confusion metrics of the hybrid fusion models, which shows strong diagonal dominance, which means the high true positives, and some of the confusion still remains with the QPSK and 16 commas better than other 4 models, which shows the best resilience under under channel interference. The best takeaway from this is the hybrid fusion model handles complex interference conditions and better than recurrent and hybrid baseline models and matches slash exceeds the VGG robustness. Now we conclude my presentation with the following points. Hybrid fusion model at low SNR achieves for about 66.72 accuracy at low SNR of -20 dB, far surpassing conventional models. Hybrid fusion model demonstrates exponential robustness in noisy environment. Hybrid fusion model at high accuracy reaches about near perfect accuracy of 99.97 at strong signal conditions. Hybrid fusion model has the following key advantages: that which uses late fusion architecture, which enables powerful feature integration. It uses a meta classification and transfer learning or channel interference dataset, further robust its effectiveness. Hybrid fusion models set a new state-of-the-art automatic modulation classification, especially when viewed in low SNR and interference-prone scenarios where all other conventional models cannot do so. The following are the references that I use as a literature review.